Hi everyone, welcome back. In this video, we are going to understand one of the most important concepts in SQL Server performance engineering, indexes. In the previous video, we learned that SQL Server stores data inside pages, and we also saw that without indexes, SQL Server may need to scan thousands of pages just to find a few matching rows. So naturally, the next question becomes, how does SQL Server avoid scanning everything? The answer is indexes. Indexes allow SQL Server to navigate directly to the required data instead of checking rows one by one. Small example. Let's start with a very small example. Suppose we have a sales line table with only a few rows, and each row contains sales ID, item ID, and quantity. Now imagine we execute a query searching for sales ID equal to SO-1004. Without index. Now suppose there is no index on sales ID. What does SQL Server do? It starts checking rows sequentially. First, SO-1001, not matching. Then SO-1002, still not matching. Then SO-1003, still not matching. Finally, SO-1004. This process is called scanning. SQL Server keeps reading rows until it finds the required data. Now, with 5 rows, this is fine, but imagine millions of rows. The cost becomes extremely expensive. Adding index. Now let's add an index on sales ID. An index creates a searchable structure. Instead of checking rows sequentially, SQL Server can now navigate directly toward the matching value. Internally, the index stores indexed values, along with pointers to the actual data rows. So SQL Server can quickly jump to the correct location. This dramatically reduces page reads, I/O operations, and execution time. Scan versus seek. One of the most important concepts in SQL performance is understanding the difference between a scan and a seek. A table scan means SQL Server reads many rows or pages sequentially. An index seek means SQL Server directly navigates to the matching rows. Seeks are usually much faster because they minimize unnecessary I/O. Clustered index. Now let's understand clustered indexes. A clustered index determines the physical order of data inside the table. This means the actual rows are stored in sorted order based on the clustered index key. For example, if sales ID is the clustered index, rows may physically be stored like SO-1001, SO-1002, SO-1003, and so on. This makes range lookups extremely efficient because nearby rows are stored close together physically. And importantly, a table can have only one clustered index because data can only be physically ordered one way. Non-clustered index. Now let's compare that with a non-clustered index. A non-clustered index is a separate structure. It does not physically reorder the table data. Instead, it stores indexed values along with pointers to actual rows. So SQL Server first navigates through the index, finds the row pointer, and then jumps to the actual data row. This works very similarly to a book index. The index tells you where the information exists, but the actual content is stored elsewhere. And unlike clustered indexes, a table can have multiple non-clustered indexes. Selectivity. Now, not all indexes are equally useful. Indexes work best when filtering returns only a small subset of rows. This concept is called selectivity. For example, sales ID equals SO-50000 usually returns very few rows. That is highly selective. But filtering on something like status equals open may return thousands of rows. That is low selectivity. And low selectivity indexes are often less effective. Real D365FO example. Now let's connect this back to D365FO. Suppose we have 100,000 sales line rows. Without an index, SQL Server may need to scan thousands of pages. But with a proper index on sales ID, SQL Server may only need to read 2 or 3 pages. That is a massive reduction in physical I/O. And this is exactly why indexes are so critical in ERP systems. Closing. So the key takeaway from this video is, indexes exist to reduce physical page reads. Instead of scanning entire tables, SQL Server uses indexes to navigate quickly toward matching data. And fewer page reads means faster queries, lower I/O, and significantly better scalability. Clustered indexes determine physical row ordering. Non-clustered indexes use pointer-based lookups. And in the next video, we'll go deeper into how indexes are internally organized using B-trees. So I'll see you in the next video.